Okay, today we are going to be learning about tree diagrams and counting principle. Okay, tree diagrams you're probably familiar with. I imagine you've seen this somewhere, somehow, someplace in your math education, but it still warrants a little bit of a review. And then counting principle is kind of like the tree diagram shortcut-ish. So there are 4 pages of notes today, but there's no practice. So we'll do all of it together and then you're done. So I know it's long, but I promise you won't have to do anything by yourself. So hopefully that's a good trade. So let's go ahead and look at tree diagrams. It says, in many cases, there is more than one action or choice, which results in several outcomes. Tree diagrams are a useful tool to organize and show all the possible outcomes. Okay, so the reason it's called a tree diagram is because it ends up kind of looking like an upside down tree, I guess. You guess you could make it right side up, but you'll see it, you'll get it when I show you. All right, so we're going to start with example 1. It says the spinner below is spun twice. Cool. So the first time you spin, your choices are A, B, and C, right? So then if you were to spin a second time, we'll use red for our second time, you would have A, B, and C, A, B, and C, A, B, and C, right? Those are all the possible things that you could get if you spun it twice, right? So if we look at this, and I'm going to use yellow to show the different combinations, we could have AA, oops, we want that in highlighter. We could have combination AA, combination AB, combination AC. And then we could do the same thing for the B's and the same thing for the C's. Okay, so that just helps us because if I asked you what are the possible combinations, I mean, you could spend a lot of time in your mind trying to write them out. And then also, what if you duplicate one, or what if you forgot one? And AC is not the same as CA, so those are different orders of things happening. So that's why we use tree diagrams. Okay, so then if I was to go over here and list my sample space, those are the possible outcomes I could have. Remember, we had the fancy bracket. So I've got AA, AB, AC, BA, BB, and BC. And then I've got CA, CB, and CC. So those are my sample, that's my sample space. Those are the possible things, the 9 possible things that could happen if I were to do that spinner twice. Okay, so then we can use this sample space to answer our probability questions, right? So now we can just use all of these combinations to help us answer what's going to happen. What are our possible probabilities? So what's the probability that you get B twice? Well, simple enough. We only have that one time, right? So our answer here would be 1 out of 9. Okay, because the combination of BB only happens once. All right, so what's the probability that you would get A at least once? Okay, so I'll use red highlighter for that. So I've got AA. That counts because it says at least once, not only once. AB, AC, BA, CA. So that happens to be 4 out of 9 times that could happen. Oh, I'm sorry, 5. Woo. Guys, I really can count. 5 out of 9 times. And then what's the probability of getting no C? So there's not a single C in the answer. So first, let me erase some of these other highlighter. Oh, that's fun. That wasn't supposed to happen. Okay, let's just we'll use gray for this one. That doesn't have a C. Okay, so we have 1, 2, 3, 4. We only have 4, right? Only 4 of those don't have a C in them. So 4 out of 9. Now, if we didn't have our tree diagram and to use to make our sample space, that could have taken us a lot longer to figure out those probabilities. Okay, so it takes a little bit of work up front, but then it makes the actual probability questions pretty easy. All right, let's do another one. Oh, you know what I'm going to do really quick is I'm going to show that we used green for this, we used red for that, and we used gray for that. Okay, just in case you look back on and you're like, what was Mrs. Marsh doing with those? Okay, so now let's talk about this next example. The popcorn stand offers buttered or unbuttered popcorn in 3 sizes, small, medium, and large. All right, so our first choices are buttered or unbuttered. That's what we're going to do. And then we can do small, medium, large, small, medium, large. Right, so now we know exactly what the possible combinations are. So our sample space is going to be buttered small, buttered medium, buttered large, unbuttered small, unbuttered medium, unbuttered large. Okay, so smaller options, right? Because we only started out with 2, and then each of those was connected to 3 choices. Okay, so what we have here now, super easy. Probability of having buttered popcorn. So let's use green again for our highlighter. So we have 1, 2, 3 things that happen to be buttered. So our answer for that is going to be 3 out of 6, which is 1/2. Okay. And then what's the probability of having large? So let's use our red highlighter again for that. So probability of large popcorn is going to be 1, 2. Because only 2 of those combinations actually is a large size. So that's going to be 2 out of 6, which is 1/3. And then what's the probability of having a small with no butter? So we'll use our gray highlighter again for that. Unbuttered small, there's only 1 of those that occurs. So then my answer would be 1/6. Right? Oops, and I forgot to do this one in green. Okay, so again, a little work up front, but it pays off when it comes to those probability questions. All right, let's do another one. You have a choice of vanilla or chocolate ice cream, and you can have it topped with sprinkles, peanuts, granola, or M&Ms. All right, so let's make our tree diagram. We have vanilla or chocolate, and then we can have sprinkles, peanuts, granola, M&Ms, sprinkles, peanuts, granola, M&Ms. So then our sample space is going to be vanilla sprinkle, vanilla peanuts, vanilla granola, vanilla M&Ms, chocolate sprinkles, chocolate peanuts, chocolate granola, chocolate M&Ms. So there's our sample space. And I'm sorry, my brackets are just terrible today. There we go, that's a little better. Okay, and that granola one looks really bad. Chocolate granola, let's fix that. Okay, so what's the probability of having chocolate ice cream? So here we go, we'll use our highlighter again. We'll use green, probability of chocolate. So we have 1, 2, 3, 4. And our total is out of 8, right? So we're going to get 4 out of 8 of the combinations, which is half of those could happen. So then what's the probability of having M&Ms as a topping? Well, we have 1, 2. 2 of those outcomes have M&Ms, so that's going to be 2 out of the 8 possible outcomes, right? Because each of those pairs makes an outcome, which simplifies to 1/4. And then what's the probability of vanilla with sprinkles? There's only 1 of those combinations. So my answer is going to be 1 out of 8 of those combinations. Okay? I'm just going to leave that there for a second. In case you need some time, you can pause it and copy down what you need. And then we'll go on to our next few examples. Okay? So on page 2, we have just a couple more examples of tree diagrams. A day of the week is chosen at random, then a coin is tossed. Cool, cool. All right, so we've got our days of the week. So we've got Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. And then we're going to flip a coin. And we know that when you flip a coin, you either get heads or tails. Gets a little cluttered here. right? So when we do our sample space, okay, we're going to write down all those possible combinations. So this is going to be kind of heavy here. So I'm going to zoom in as best I can and try to get all of these in here. Oopsies, we don't want red, we want blue. So we've got Monday heads, Monday tails, Tuesday heads, Tuesday tails, Wednesday heads, Wednesday tails, Thursday heads, Thursday tails, Friday heads, Friday tails, Saturday heads, Saturday tails, Sunday heads, Sunday tails. There we go. So we have all of our possible combinations there, okay? And I'm sorry that it looks a little wonky with the sun and the sat and the th and the t, but I think you guys know what's happening here. All right, so we know what each of those stands for. All right, so let's find the probability of getting tails. So I'll use my highlighter. I think we were using green to start with. So I'm going to find all of the combinations that has a second letter of the T. So I've got Monday tails, Tuesday tails, Wednesday tails, Thursday tails, Friday tails, Saturday tails, and Sunday tails. So that is going to be 7 out of the possible 14 outcomes, which then simplifies to 1/2. Remember, guys, I don't want you doing anything other than fractions. We're totally avoiding the decimals and the percents. Okay, how about the probability of a day, something happening with a day that starts with a T? Cool, cool. So let's use our red highlighter here. So we've got Tuesday heads, Tuesday tails, Thursday heads, Thursday tails. All right. So now we've got 4 out of 14 chances that that can happen, and that simplifies to 2/7. Right. And then our last one is the probability of a Friday and heads. All right. Boom. It only happens once, guys. Right? Only one time could it possibly happen where you would choose the Friday and then also flip a coin and get heads. So that's going to be 1/14. Right? Okay, so now let's look at our next example. The spinner below is spun. Then the letter from the word math is chosen at random. So if you look at the spinner, it's basically just got, if I zoom in here, it's got different names of shapes. Cool, huh? Really fun. Okay, so let's go ahead and try to do our tree diagram here. So we've got trapezoid, we've got parallelogram, we've got rectangle, we've got rhombus, we'll use RH, and we've got square. And then a word from math is chosen. Sweet. So we need 4 little things for each of these. Okay, and then we write in M-A-T-H, M-A-T-H, M-A-T-H. You guys over this yet? M-A-T-H, M-A-T-H. Whew. All right, so we can see all of our possible outcomes. So now we're going to go over here to our sample space. We've got our bracket, and we've got, what did we start out with? Trapezoid. So we've got trapezoid M, trapezoid A, trapezoid T, oops, trapezoid H. Then we've got rectangle M, rectangle A, rectangle T, rectangle H. Then we've got, oopsies, I totally forgot parallelograms, guys. Let me erase that really quick. I'm going to go ahead and pause the video, and we can all fill these in separately, and then you can check your work. So I'm going to pause this real quick. Okay, so there you go. It's all finished. I took every single shape and matched it up with the letters from M-A-T-H, right? And I've got my sample size here. Now I'm ready to do my super easy probability. Probability of having the letter M. All right, so we'll use our highlighter here. Use green again. So let's highlight where we see the letter M. Well, 1, 2, 3, 4, 5. Okay, so we have 5 times out of 20 possible. So that's going to be 1/4 is the probability. How about probability of a shape with 4 congruent sides? All right, well, to my recollection, a rhombus has 4 congruent sides, and so does a square. So I'm going to highlight anytime that I see a rhombus or a square. So I've got rhombus, 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 square, 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 square. So that tells me that there are 8 out of 20. That's the probability, which would be 2/5, right? So there's a 2/5 chance that if you spin the spinner and then choose a letter out of a bag, it might be a rhombus or a trapezoid. Okay. And then here we go. A 6-sided die is rolled and the spinner below is spun. Okay. Oh, I didn't finish the last probability. Guys, I'm sorry. I got so excited about the squares and the rhombi. All right. So, trapezoid, then not an A. Yikes. Okay. So trapezoid and then not an A would give me 1, 2, 3. Only 3 times that's going to happen out of the 20. Because only 4 of the times it's a trapezoid, and then 3 of the times is also not an A. All right, now we can move on to this die here. So we've got a standard 6-sided die, and then the spinner is spun. So we've got 1, 2, 3, 4, 5, 6. All of those could happen. And then we've got red, blue, yellow, 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 and red, blue, yellow. So those are all the possibilities that could happen. So I'm going to do the same thing again. I'm going to freeze the video. I'll start out the sample space and then I'll freeze it and you guys can check your work. So my sample space is going to be 1 red, 1 blue, 1 yellow. 2 red, 2 blue, 2 yellow. Okay, I'm going to pause it and we'll reconvene. Ta-da, it's like magic, right? So now you have your sample space, all the possible combinations of things that could happen if you roll a die and then do the spinner. Okay, so let's go through again and find our probabilities, which again is going to be super easy because we have everything mapped out. So the probability of having a prime number. All right, so first let's refresh our memories, which are the prime numbers, right? So the prime numbers in this group are 2, 3, and 5. Remember, 1 is not considered prime, okay? It's considered a special number. It has its own little meaning. And then, 2, 3, 5. Yeah, 2, 3, and 5. 2, 3, and 5 only have 2 factors, itself and 1. Okay, so our prime numbers are going to be all the 2s, all the 3s, and all the 5s. So that ends up actually being 9 out of the 18 possible outcomes. Okay, oh, look at that. Probability of being red. This is where we've been using our red highlighter. That's pretty convenient. So we have 1, 2, 3, 4, 5, 6 combinations that happen to be red. So we have 6 out of 18, which simplifies to 1/3. All right, and our last probability is saying at least 3, then yellow. Okay, so it has to be at least 3, which means 3s count. So the 3s, 4s, and 5s, then yellow. So we've got 3 yellow, 4 yellow, 5 yellow, 6 yellow. So that means that there are 4 possibilities out of the 18, which simplifies to 2/9. Okay, so those are tree diagrams. Pretty exciting. Now we're going to move on to counting principle, which I think you will find way easier and way quicker. So let's move on to page. Let me shrink this down in case you need to freeze the screen for a second, and then let me go on to page 3. Counting principle. You can use the counting principle to find the total number of outcomes. If one activity occurs in M ways, and the other activity occurs in n ways, then both activities concur in m times n. Okay, so that seems like a lot of gibberish right now, but trust me, you're going to be like, oh, this is so easy. I love the counting principle. It's my favorite. Okay, so example number 1. To leave her office, Karen can choose... Karen. That makes me laugh because I keep seeing all these memes about Karen. Anyway, Karen can choose between 3 sets of stairs and 7 doors. How many ways can she leave her office? Well, she has 3 sets of stairs and 7 doors, so she has 21 ways she can leave her office. And that's our answer. So we took the 3 times the 7, got our answer. Right? Is that like the easiest thing ever? Okay. A sweater comes in 4 sizes and 8 colors. So we've got 4 sizes, 8 colors. How many different sweaters are possible? 4 times 8, 32, right? Some of you are probably thinking, why didn't I just use this instead of tree diagrams? Okay, well, the difference is this is only asking us for outcomes. If we needed to know the probability of a certain way that Karen left the office or a sweater that I wanted to purchase, then you need your tree diagram so you have the specific combinations. This is just telling us how many outcomes there are. Okay, so that's why you can't always use this, but if all we're asking is for how many things are possible, if it's not asking for the probability of something, this is your strategy. Okay, a class has 11 boys and 16 girls. How many ways can the teacher choose 1 boy and 1 girl? 11 times 16 equals 176. Let me redo that equal sign. It looks like a negative, and I don't want any confusion. Okay, a dinner menu consists of 5 appetizers, 12 entrees, and 3 desserts. How many ways can someone order 1 appetizer, 1 entree, and 1 dessert? All right, 5 times 12 times 3 is going to give you 180 different combinations, you guys. In the past, I challenged the classes, and there of course were ways to cheat it, but to find out how many combinations of a sandwich you could make at Subway, I mean, think about it. How many types of breads and cheeses and toppings and meats and veggies and, I mean, toasted, not toasted. There were like a bajillion different ways. I mean, I think it's in the hundreds of millions possible sandwich combinations you could get at the Subway. So you're welcome for that bit of information. A card is chosen from a standard deck, then a die is rolled. Okay, so if you remember from previous examples, there are 52 cards in a deck, and there are 6 numbers on a die. So we would get 52 times 6, which means there are 312 possible outcomes that could happen. Okay. A quarter is tossed, and then a letter from the word snowflake is chosen. How many outcomes are possible? Well, we have 2 outcomes when we flip a quarter, and we have 9 letters in the word snowflake, so that would be 18 possible combinations. A day of the week is chosen, then the spinner to the left is spun twice. How many outcomes are possible? Okay, so we have 7 days of the week, and it looks like on that spinner there are 12 letters, and then we have to do it twice. So 7 times 12 times 12, and we get 1,008 possibilities. Those are how many outcomes. So day of the week, so that's 7, and then the spinner is twice, so the 7 times 12 times 12. All right. How many ways can someone randomly dial a 7-digit phone number? Oh my gosh, you guys. So this one's a little bit different, okay, because, well, first of all, how many digits are there, right? So if you count, you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are actually 10 digits. 0 does count as a digit, right? So we've got 10. And then if you have a 7-digit number, that means, and it says, it doesn't say anything about not duplicating. So you've got those 10 digits, and you're going to be doing 10 times itself 7 times. So we're just going to use our exponential, right? Because we've got 10 digits times 10 digits times 10 digits times 10 times 10 times 10 times 10. So we all remember that our shortcut is to just take 10 to the 7th power, right? And so your answer is actually 10 million. There are 10 million combinations of randomly selecting a 7-digit number. 10 million. That's a lot, right? Okay. A quiz contains 5 multiple choice questions. Each question has 4 answer choices. How many ways can the questions be answered? All right, so we've got 4 choices, right? So that's going to be the thing that we can choose from, and that's going to be 5 different times, right? So we've got, if we were to do a tree diagram, we would have ABCD, and that would be multiplied ABCD times ABCD times ABCD. It'd be a giant tree diagram, right? So we'll just stick to the counting principle, and we'll say that that's 1,024 combinations to answer the quiz. Aren't you guys glad that you study for stuff? Because that's a lot of different things that you could do wrong. All right. The library codes their books using 2 letters followed by digits 0 through 9. How many different codes are possible? Woo! Okay, so how many letters in the alphabet? 26. And then times 26 because it's 2 letters. And then we have followed by a digit 0 through 9. So that's going to be times those 10 digits that are possible. I understand it's confusing. 10 is not one of the values, but there are actually 10 single digits when you consider 0 as one of those single digits. So if we did 26 times 26 times 10, you're going to end up with 6,760 possible ways to put labels on those library books. Okay, one more page. You guys are doing awesome. Let me shrink this down so you can copy, make sure you have everything filled in. And let's go on to our last page for today. And then remember, the reward is that you don't have any practice by yourself. Woohoo! Patrick is buying a new car. He can choose the body style, color, and engine type. If there are 54 ways he can select a car with 3 body styles and 2 engine choices, how many colors are available? Okay, so we're going to work a little bit backwards here. All right, so he knows he can have 54 choices, right? We know that there are 3 body styles, 2 engine choices, times what will give us 54, right? So we're going to use our variable here because we don't know how many colors there are. That's what we're trying to solve. So then we end up with 6x, equals 54. We have our little one-stepper, so you find out x equals 9, so there are 9 color choices. All right, so we worked backwards there. Okay, school cafeteria, you can choose 1 sandwich, 1 snack, and 1 drink. The number of drink options is equal to the number of snack options. If there are 63 ways to choose your lunch with 7 different sandwich options, how many drink options do you have? All right, so we know that drink options are the same as snack options. Cool. And they only told us the sandwich option. There are 7. So our equation for this is going to look like this. 7 times the number of drink times the number of snack, and they can both be represented by x because they are the same value, and we know that's going to equal 63. So really what we end up with then is 7x squared equals 63. We're going to divide by 7 on both sides, so you end up with x squared equals 9. And then think back to your Pythagorean theorem days. Square root of x squared equals square root of 9. So you're going to get x equals 3. So that tells us there are 3 drink options and there are 3 snack options. Okay, so how could you check your work here? What could we do to make sure that is accurate? You're right. You could put the 3 back in for the x's. 7 times 3 times 3 is 63. So that's how you would know you were correct. All right. Now we've just got some examples to do here. Okay. We're just zipping right along here. A coin is tossed 3 times. What is the probability of getting heads just once? Okay, so our possible outcomes we know is going to be 2 times 2 times 2, which is 8 outcomes. But that's not our final answer. We want the probability of getting heads just once. So we're going to draw a tree diagram. And it's tossed 3 times. So we have heads, tails, and then heads, tails, heads, tails. Let me move this one over here. So we've got tails, and then you flip it again and you get heads or tails, and then you flip it again and you get heads, tails, heads, tails. So what's the probability of getting heads just once? So let's look through here. Nope, that has 2 heads. Or that has 3 heads, so that's not it. Heads, heads, tails, that's not it. Heads, tails, heads, nope. Heads, tails, tails, that could be just once. All right. And then it looks like tails, tails, heads only has heads once. So the probability of that happening, oh, I'm sorry, tails, heads, tails. So it looks like the probability of that happening would be 3 out of the 8 times. Okay, let me, hold on a second. Let me get rid of this highlighter again. Okay, so what I'm doing here is I'm looking, just to make sure everybody understands, I'm looking at this, it says heads, heads, heads. So that's not going to be an option. And then I have heads, tails, heads, heads, tails. Nope, that's not going to be only heads once. Heads, tails, heads. Nope, that's not going to be it. Heads, tails, tails. Yep, that's going to be one of the outcomes that only has heads once. So then I would go back here and I'd say tails, heads, heads. Nope. Tails, heads, tails. Yep, that's going to be one of them. Tails, tails, heads. Yep, that's going to be one of them. And then tails, 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 no. So if I look at the 3 that I circled that are also still highlighted, I get 3 out of 8 that fit that criteria. Okay? And I knew my denominator was going to be 8 because I used the counting principle to come up with how many possible outcomes there were. All right, number 14. A month is chosen at random, then a standard die is rolled. What is the probability of getting February, then a number less than 5? Okay, so I've got 12 months times 6. So I'm going to get at least 72 outcomes. So that's going to be my denominator. Okay. Well, February, if I do February only, so we've got February is the only month that starts with an F, so that's easy. And then we've got 1, 2, 3, 4, 5, and 6 on the die. We don't need to draw out all of the months because we only need to do the one. We know that there are 72 outcomes, so we know what our denominator is going to be. And then the question is a number less than 5. So it looks like we would have February 1, February 2, February 3, February 4. So there are only 4 out of 72 would be our probability, which then of course we could simplify to 1/18th probability that you would get February and a number less than 4. Okay, just a couple more. A card from a standard deck is chosen at random, then a coin is tossed. What is the probability of getting an ace and then tails? All right, so we know that there are 52 cards times 6, or excuse me, times 2, because you're either going to get heads or tails, right? And we know that we could get ace of hearts, heads and then tails, ace of diamonds, heads and then tails, ace of spades, heads and then tails, or ace of clubs, heads and then tails. So what's the probability of getting an ace and then tails? So that is going to be ace of hearts tails, ace of diamonds tails, ace of spades tails, ace of clubs tails. So let's go back up here. We didn't finish this. I'm sorry, there are 104 possible outcomes. And we know that 4 of those are going to be an ace with tails. So then we simplify that to 1 out of 26. There's a 1 in 26 chance that that will happen. Okay. A standard die is rolled 2 times. What is the probability it lands on 1 both times? Well, we've got 6 times 6, so that's going to give me 36 outcomes. And then the probability that I'm going to get a 1 both times is just going to be 1 time. There's only 1 chance of getting a 1 and then a 1. Everything else is not going to have double 1. So it's going to be 1 out of 36. Pretty easy stuff. All right, 17 and 18. Each spinner to the left is spun twice, okay? So we have some colors and we have some numbers. What's the probability of getting a yellow and an even number? First of all, we need to find out how many outcomes we have. 5 times 8 equals 40 outcomes. Okay, and then we could get yellow, and then we could get 2, 4, 6, or 8. Right, yellow and then an even number. So that is 1, 2, 3, 4 out of 40 times. So my probability is going to be 4 out of 40, which simplifies to a 1/10 chance. Okay. I don't need to find the probabilities of red and orange and green and blue in even numbers. I just want yellow. So I'm basically just taking a little part of my giant tree diagram and I'm figuring out what that probability would be. And I can do that because I know the outcomes. I used my counting principle for the outcomes. What's the probability of getting orange or blue and a multiple of 3? All right, so again, my outcomes is going to be 40. So that is my denominator for my probability. And I've got orange or blue and a multiple of 3. So that's going to be orange 3, orange 6, blue 3, blue 6. So that means I have 1, 2, 3, 4 chances of that happening. So my probability here again is going to be 4 out of 40, which is 1/10. And again, I didn't have to do the red and the yellow and the green and the multiples of 3 because those aren't going to be anything that I would use, so I wouldn't end up even needing to connect them, right? Okay, guys, that's it. Those are your notes. I know they were long. I'm sorry they were so long, but you don't have to do anything by yourself right now. So think of it as us having done the notes and your practice by yourself, and now you're done. All right, I hope you have a wonderful weekend, and then you guys, we only have 6 days left, and then you're in high school. It's crazy. All right, bye, guys.